Transformation. Transformation is an important section in the course of graphics and visual computing. In today's lecture, we are going to introduce transformation and see different classes of transformation. Introduction to transformation and class of transformations. In our previous lectures, what we had seen how the polygon surface data structure is stored. We have a vertex table, an edge table, surface table, and these surface tables form the object table. And we link the vertices to the edges. The edges, ensemble of edges would link to surfaces, and multiple surfaces would link to objects. In this, we had developed a B representation linked list which represented the structure, the hierarchy of the structure, starting with the vertices, going to the edges, from the edges to the surface, and selecting multiple surface as part of the system. What we see is that when we have an object, the transformations that we need to do, be it placing it in the world coordinates or changing it to the camera coordinates or to the screen coordinates or animating the object, the transformations take place at the lowest level, that is at the vertex level, and rest of the structure of the objects remains the same, and they link to the modified vertices, and in this manner the modified objects are displayed on the screen. The outline of the sections on transformation would be introduction to transformation. I would also discuss in this lecture class of transformation. In my future lectures, I will be taking up representing transformation, combining transformation, and change of orthonormal bases. So let us begin with introduction of transformation. What is a transformation? Transformation maps a point x and y in one coordinate system to a point x prime, y prime in another coordinate system. In two dimension, I will have two equations like x prime and y prime, which can be written as axy plus bxy plus tx, while y prime will be equal to ayx plus byy plus ty. The same equation, if we see them in three dimension, we have this quantity, a third equation is added, and the main structure of the equations remain the same, but I have a cxz, cyz, and czz is added to this. We see that there is a constant tx, ty, and tz added to these equations. This is responsible for the translational transformation of the object. Now, we could represent the same equations in a matrix format, and in two dimensions, this matrix looks like x prime, y prime, a vector, will be equal to a matrix ax, bx, ay, by multiplied by a vector x and y plus a translational vector tx, ty. The same equation in three dimension would be of this kind, where the matrix now, instead of being a 2 by 2 matrix, becomes a 3 by 3 matrix, and the vector becomes of a three coordinates x prime, y prime, z prime, and x, y, z, and the translational vector is tx, ty, and tz. So what we see here is a point where I'm varying my x, y, z of this point, and I'm creating this animation of this point. But what we also see is that the coordinate system is also rotating as this point is moving. So there is a two-way transformation. There is a transformation of the coordinate system, and there is a transformation in the position of the point in this case. Normally, any object that we have is designed in the local coordinate. As we see here, the cube and the pyramid. This is then all these objects are placed on a common platform called the world space, a common to all objects. This world space is transformed into the eye space or camera space derived from the viewing frustum. That is, from the it depends on the direction from where we are looking at the world. Then finally, the camera or the eye space is converted to the screen space, and in the screen space we need to index accordingly to the hardware attributes, that is the resolution of the screen and so on and so forth. Now we have seen these objects earlier in our previous talk, where we took help of these objects to represent the different objects which were made with different coordinate systems and then placed in a world coordinate, which was shown here by its three places. These objects were translated, rotated to place these objects in a specific locations. Now I take the same objects and let us see further. Now if I mark the Rubik's Cube, let me take the first object and let me mark the vertices or just the corners of this Rubik's Cube to represent this cube, and where I'll have this V1, V2, V3, V4, V5, V6, V7 and V8 coordinate systems, and this forms my skeleton model of the cube. Now if I remove away all other objects and the image of the cube, it remains, the cube remains and the vertices remain. And what we see here is that this cube has been translated by a coordinate tx and ty from the origin and has been rotated by an angle theta around its object axis. So let us see the vertices. Here I have my 8 vertices, and these 8 vertices forms my vertex linked list. Above this vertex linked list is my edge linked list, where I have got E1 connecting V1, V2, E2 connecting V2, V3, E4 connecting V1 and V4. It forms the top square. Similarly, if I take the other coordinates, it forms the other edges of the cube, and in total I have totally 12 edges, which describes my cube. Please note here I have used E1, E2, E3, E4 for the upper square, and E5, E6, E7 as the edges for the lower square, and the segments or the edges that is joining the upper square and the lower square is defined by the edge E9, E10, E11 and E12. Now these edges are connected together to form surfaces, S1 being the top surface of the cube. Similarly, I will have the other surfaces S2, S3, S4, and S5 and S6, and S6 being the surface of the lower lower square of the cube. Now these surfaces together forms the first object, the object 1. And similarly, we had other objects, like the second object was the bottle of sanitizer, and we had another complex objects which we had in our previous photograph. Now this forms the object linked list. So let us continue with object 1. So to bring this object 1 to the world coordinate system, we need to translate it by tx and ty and rotate it by an angle theta. Now to apply this transformation of the object, what we need to do is that we need to change the position of v1, v2, v3, v4, v5, v6, v7 and v8. So the transformation, though shown acting on the object, it really acts on the lowest level of the object, that is the vertex table. So the transformation that we will be talking about is transformation of points or vertices from one position to another position. As we had shown previously in this equation, the generalized equation of transformation. We will take up simple transformations first. We have the identity transformation, the translation, the rotation, and scaling. The scaling could be isotropic. Also, it could be anisotropic or ununiform. What we see is that these transformations can be combined. Are these operations invertible? Yes, except for scaling equals to 0. Because scaling equals to 0 would mean that an inverse transformation would mean a division by 0, which is not possible. The translation transformation. Translation by tx, ty, and tz in 3 dimension. This could be in 2 dimension thought to be a translation in tx and ty only. In my previous example, the object was translated only in 2-dimensional. The 3rd dimension was not translated, but there was a rotation around the z-axis. So this translation can be applied to a 2D and a 3D graphics object. What does it do? It moves the origin by an amount of tx, ty, and tz. It does not distort the object, slides the drawing around in the Cartesian space, that is, moves the object without distorting from one position to the other, is what is meant by translation. Now rotation. We need to rotate by some angle. The angle is in radians. Remember, a full rotation is defined as 2 pi radians, and this can be applied to 2D as well as 3D graphics. Rotates or twists the drawing around. Convention is that a positive angle is from positive x-axis to positive y-axis. So effectively you can imagine it to be a right-hand rule or an anti-clockwise direction from the x-axis moving towards the positive y-axis. And this could be confusing if y is downwards, as we have seen that normally for a screen the y-axis is considered downwards. So this has to be seen when you design the graphics, is what frame of reference are you using? Are you using a y-axis which is pointing downwards, or the y-axis is pointing upwards? Now if I have a point Vx of y, which could be represented by its projection in the x-axis as x and y, and it makes an angle phi with the coordinate system, where the distance from the origin of the coordinate is r. So I could write this vector v of xy as x is equal to r cos phi and y is equal to r sin phi. Now we would like to rotate this point or this vertex from the point vxy to a point v prime xy, and the rotation angle is theta, which would give me a new coordinates to this vertex. The new coordinates are x prime and y prime. Now if I would like to write these coordinates of this vector v prime in the similar manner as I have written for the vector v of xy, I would have x prime would be equal to r cos phi plus theta, and y prime will be equal to r sin phi plus theta. Now the angle is a combination of two angles which, using trigonometric identity, can be separated out, where x prime equals to r cos phi cos theta minus r sin phi sin theta, while y prime is equal to r sin phi cos theta plus r cos phi sin theta. If we notice these two equations carefully, we see that r cos phi is equal to x and r sin phi is equal to y. Now, and obviously if we replace these quantities by the first set of equations, we get the final coordinates or final equation of x prime and y prime in function of x and y, which is a linear superposition of x and y biased by a trigonometric function of sine and cos. So these equations can be written again in a matrix format, and the matrix format could be written as in two dimension as here, which is given as x prime y prime is equal to cos theta minus sine theta cos theta multiplied by the vector x and y. Please note here that there is a sign change in the first line, that is minus sine theta, which is there here. Even though sine theta and cos theta are nonlinear functions of theta, x prime is a linear combination of x and y prime is a linear combination of x and y. What is the inverse transformation? Rotation by minus theta, that is a rotation r to the power minus 1, is effectively r transpose. This can easily be proven. Cos cos of minus theta is equal to cos of theta, while sine of minus theta is equal to minus sine theta. So here there is no sign change. Here there is a sign change. And minus theta. So since the position of minus sine theta and sine theta are swapped, so R inverse is equal to R transpose. Now if we try to move from a 2D to 3D coordinate system, it essentially means that the rotation is in the two-dimensional plane, but the rotation axis is the z-axis. So the matrix remains similar, but I have a z column and added, where I have 1, so add for z. So z prime is equal to z. There is no change in the z coordinate. There is only change in the x and y coordinate. But what we see here is that we have an axis of rotation around which this rotation takes place. In the previous case, there was a rotation, but the rotation was perpendicular around the axis, perpendicular to the plane xy. So here again the z-axis is being the perpendicular coordinate. The rotation is around the z-axis. Now we could find a rotation around the other axes. We could rotate around the x-axis or y-axis or z-axis. In this case, if we rotate around the z-axis, is given here, which was shown earlier. If I rotate it around the x-axis, the matrix changes, and if I rotate around the y-axis, the matrix is shown as it is here. Please note that picturesquely, if you see that the minus sine theta which was there on the first row has moved to the last row. The sign flips. Next we come to the scaling transformation. Scaling a coordinate means multiplying each of its component by a scalar. Uniform scaling means this scalar is the same for all components. That is, you enlarge the x-axis by the same amount, enlarge the y-axis by the same amount, and enlarge the z-axis by the same amount. Here in this figure, what we have done is that we have enlarged the x and y axis by 2, and the house which was drawn has enlarged or increased by 2. But for a non-uniform scaling, different scalar is multiplied for different components. Here what we have done is that we have multiplied the x-axis by 2, while the y-axis has been multiplied by half. So what you see is that the house has been broadened and shortened. The height has decreased by half, and the width of the house has increased by double. So this is a non-uniform scaling or anisotropic scaling, while the previous case, this is called an isotropic scaling, and this case is an anisotropic scaling or a non-uniform scaling. The scaling operation can be written as x prime is equal to ax plus by, which could be written in two dimension as a matrix x prime y prime is equal to the diagonal elements ab, and the non-diagonal elements are 0. And for isotropic translation, what we have is that a has to be equal to b. So now the similar equations, if we do it in 3 dimension, we need to add a third quantity. Z prime is equal to Cz, and the matrix changes in this manner where I have the diagonal elements A, B and C. And what is the inverse of S? The inverse of S can exist if A, B and C are not equals to 0. And for isotropic scaling or for uniform scaling, A has to be equal to B, which has to be equal to C. So scaling transform depends on 3 quantities A, B, C in 3 dimensions. In 2 dimension, you could scale it using 2 coordinates, 2 values, 2 scalars A and B. And this can be applied to 2D and 3D graphics. It stretches the coordinate space. One useful scaling is scale by 1, minus 1. This makes the y go up. That is to convert a screen coordinate system to a generalized coordinate system that we learn in mathematics. A scaling of 1, minus 1 could be applied. Of course, this scaling is a non-isotropic scaling because the direction of the scaling is different, though the magnitude may be the same. The other transformation is shear transformation, and in this shear transformation I could twist an object and I could have a shear in x, a shear in y and shear in z. First augment is amount of shear in the direction of x as a factor of y, and the second is an amount of shear in the direction of y as a factor of x, and the third quantity could be a shear in z as a factor of x or y. This transformation distorts the drawing space and can be applied to a 2D as well as a 3D object. So where are these transformations used? Transformations are used in positioning objects in a scene, that is modeling. As we have seen, we need to move from the object frame to the world frame, from world frame to the camera frame. All this is possible by changing the position of the objects in the scene or modeling. This is the first reason where we use transformation. Secondly, we can change the shape of the object. We can make it fatter, thinner, or enlarge it isotropically. We could rotate the object. We could also create multiple copies of the object. We could project the object for a virtual camera. We could also use transformation to animate the object. For all these purposes, we require to apply transformation on the vertices. This was the introduction to transformation. Now let us try to put the transformation into perspective, into a proper domain, by looking at it as a class of transformation. So let us define a few classes of transformation. I have the first class of transformation, which is known as the rigid body or the Euclidean transformation. This transformation assumes that the object is a solid object, and there's a solid object like this pen, and I could rotate this pen, but I can't shrink this pen. I can translate and rotate this pen without shrinking this pen because this is a rigid object. I could have the next transformation is the similitude or similarity transformation. Here I could enlarge the object, I could scale the object. So this is a similarity transformation. We will see what is a linear transformation, and we will see that some transformations unfortunately are not linear transformation, and therefore for making this transformation linear, it is necessary to make them linear. We will talk about the affine transformations, and based on the affine transformation and taking help of the affine transformation, we will try to describe the projective transformations, the transformations which is like the perspective projection or orthonormal projections, which we do. Normally a photograph is a perspective projection, and we will see how this projection is done through a transformation. So let us begin with a rigid body transformation, which is a Euclidean transformation. As I said that this pen is a solid pen. I could rotate it and I can make a copy of it, or I can translate it. So what I see from this is that this group of translation, identity, and rotational transformation preserves the distance and preserves the angle. That is, the ratios are also preserved. Next we come to the isotropic scaling. This is, I could make the object bigger or smaller. So in this case, my distances are no more preserved, but my angle is preserved because it's an isotropic scaling. If the x-axis increases by 2, y-axis increases by 2, z-axis increases by 2, and therefore the ratios of the sides remain constant. And since the ratios remain constant, the angles are preserved. Angle is nothing else but trigonometrically the ratios of the coordinates. Next, I take the other transformations, which I call the linear transformations. I see that identity transformation, rotation transformations, isotropic scaling, as well as scaling, anisotropic scaling, reflection, shear, all of these fall under linear transformation. The only transformation does not fall under linear transformation is translation. Linear transformation, linear equations are important topics in many fields, be it machine learning to computer vision to control system, and even in graphics. Linear system plays an important role. What is a linear system? Linear transformation depends on two hypotheses. That is, one is the hypothesis of superposition, and the other is the hypothesis of homogeneity. The hypothesis of superposition is if my function or my operation is L, and if I have got my two objects or two variables, which is P and Q. So if I have something P plus Q and I apply the transformation or the function on P plus Q, this is equal to applying the transformation or the function on P separately and adding it to the transformed or applied function on Q. So it is called superposition. I can superpose two separately functions. It is equivalent as a sum of the two functions. The second condition is the homogeneity. If a variable P is multiplied by a scalar A, I could always bring the scalar A out of the operation as a constant, where I could write it as A times L of P. A linear function only depends on these two conditions, and you can easily prove if you would like to take a translation, that is, any equation y is equal to ax plus b, you will see that it violates these two relationship, and therefore it is a nonlinear transformation. It becomes a linear transformation only and only when b is equal to 0. Similarly, here the b is a translation, and here therefore the translation is not part of the linear transformation. And therefore, when we showed the translation coordinates, we showed it as an additional vector to the matrix. It wasn't part of the matrix multiplication, but it was separately added to the function, to the vector, after the multiplication by the matrix. If I have an equation which is given as y is equal to mx plus b, is this a linear system? This is not a linear function. This becomes a linear function only when b is equal to 0. We will define what is a linear function and try to develop. For a linear function, there are two conditions. Okay, a function is said to be linear when there is two condition. One condition number one. Condition number one is that it has to be, there is the condition of superposition. There is a condition of superposition, and condition 2 is called the condition of homogeneity. So if these two conditions are met, then we say a system or my system or my function is linear. Okay, so this is the condition. Now, what is superposition? Superposition is, if I go to question condition 1, which is superposition. So if I have a function, if I have a quantity x1 and a quantity x2 which is part of the group, then my function f of x1 plus x2 is equal to function of x1 plus function of x2. In the slide, we have mentioned this as a transformation, and my function is written as L of P plus Q is equal to L of P plus L of Q. Right. And my second condition, the homogeneity condition, is 2, is that if I have a variable x which is part of my world, and I have a scalar or a constant slash constant a, then my function f of ax is equal to f of x times a. A comes out of the function which is there. And in the slide, it is mentioned as L of AP is equal to A L of P. So these are the two conditions. What you see here, these are the only two conditions which define a linear transformation. I'm writing transformation because we are going to deal with transformations in this case. Now, if I have these two conditions, if I now take this equation y, which is equal to my function of x, which is equal to mx plus b, in that case I can have f of x1 will be equal to m x1 plus b, and f of x2 will be equal to m x2 plus b, and f of x1 plus x2 will be equal to m x1 plus x2 plus b, which can be written as m x1 plus m x2 plus b. Right? Now let me calculate the function f of x1 plus f of x2. This will be equal to, as given in this set of equations, I will have m x1 plus m x2 plus 2b. So here you see that this is 2b and this is a single b, right? So 2b is equal to b only when b is equal to 0. So we see that this function, which is an equation of a straight line, is not a linear function, right? So now if I take this function to be a variable of three quantities, and if I write this function as function of x comma y comma z, assuming the three coordinates, and which I could write it as a x plus by plus c z plus some tau or t. This is my function. If this is my function, this function can be proved to be a non-linear function or transformation, right? So this is a function or of a, it's a non-linear function, and this is linear. So when tau is equal to 0, it becomes linear, right? So now what you see here is that this is the condition, and this tau is essentially the translation quantity. So what we see is that we have different types of transformations, but what we see is that the transformation is not a linear transformation. And we see that it is required that we need to have a linear function for a translation. Can we sort of make translation into a linear function? Now we do that by adding an additional dimension to it. Now just let me write this transformation in a different way, in a matrix format. So I have a matrix where I have my variable x prime, y prime, and z prime, which is equal to my matrix Ax, Bx, Cx, where I could write this down here as Ay, By, cy, and this would be equal to az, bz, and cz, and this would be my x, y, and z, and I will have the translational quantity as a separate vector, which I will write it as tx, ty, and tz. Right. Now, for instance, let me assume that you see here that this is a separate vector which has been added here to to the matrix multiplication. This is the normal transformation that you have. The translation does not come as part of this matrix, but it comes as an added term or an additional term. Now, just for the sake of argument, let me just write the same equation in a different way. Okay, you will see that I will have, if I write this what I'll do is that I'll enlarge the dimension by one dimension. I'll call it x prime, y prime, z prime, and I will have here an additional dimension which I will call it w prime. So this is my vector in 4-dimension, which is there. Just I'm adding one additional dimension to it, and what you see here, I will write this again. I have ax, bx, and cx, and I have ay, by, and cy, and I will have az, bz, and cz, and I will write the fourth coordinate as 0, 0, 0, 1, and I will place my translational vector here, tx, ty, and tz, and my new matrix is of this kind, where this is x, y, z, and omega or w. So this is my new transformation. Now I'll have to show that this would be equal to this. If I can do now, this transformation doesn't have a vector which is being added to it. So this is a linear function. So, are you with me, students? So, this is a linear function, and if I take this linear function, I can write this equation. So, I will have my terms. X prime will be equal to ax x plus bx y plus cx z plus txw. I have my y prime will be equal to axx plus bxy plus cxz plus tyw, and similarly I will have here zx will be equal to ax x plus bxy plus cxz plus tz. Sorry, this is not x, but this should be all z here. Right. So this is my set of equations which I have as my condition, and if I take a specific point in my fourth dimension, a specific point being, and of course I have to write my fourth equation, omega prime is equal to omega. And what we do is that for these equations we choose a specific value of the fourth dimension, that is omega is equal to 1. And we see that these equations written here becomes similar to the equation written out here, and you have the function that it is a its translation, which was a nonlinear function, becomes now a linear function. This is called an affine transformation. This is called an affine transformation. Right. So what you have is that I linearize translation by adding an additional quantity or additional vector to it. So if I have a two-dimensional quantity like x and y, which is equal to a matrix, I'll call this prime prime, and plus x y plus a translational quantity tx ty. This is equivalent to having a quantity here which is x prime, y prime, w prime, which becomes equal to a 3 by 3 matrix here, and here it becomes equal to this matrix here, and here I will have x, y, z, sorry, no z here, I will have omega, and here I will have my, this would be my normal matrix which existed, and here I will have my tx, ty, this will be 1, 0, 0, right? So this is how I would represent a similar transformation, a translational transformation, as a linear transformation, which we will call it an affine transformation. What we have done is that we have enlarged the dimension by 1. So if my world was a two-dimensional world, it becomes a three-dimensional world, and if it was a three-dimensional world, it becomes a four-dimensional world. And from the four-dimensional world, the fourth dimensional world omega again can vary from minus infinity to plus infinity, but I will only take a specific value in the fourth dimension. That is a specific value in the fourth dimension. It will be still a three-dimensional quantity with a specific value of the fourth dimension where omega is equal to 1. So this is a mathematical jugglery to make a nonlinear function into a linear function. So if I have a translational quantity added to a function which makes the function nonlinear, affine transformation converts this function into a linear function.
Still.
Right.
There's a misnomer that any equation that follows the equation of a straight line, that is y is equal to mx plus b, is a linear equation. This is a misnomer. An equation of this kind can only be a linear equation when there is no intercept and the line passes through the origin. That is, the equation y is equal to mx plus b is linear only and only when b is equal to 0. So in multidimensional equation, I could have an equation which is ax plus by plus cz. This equation is linear, but moment I add a quantity tx to it, then the equation becomes nonlinear. A straight line equation y is equal to mx plus b is nonlinear because of the quantity b not being equal to 0, or there is a translation in the system by a quantity b which creates an intercept of b. Now, a system of this kind could be linearized by adding an additional dimension to the system. If my equation y is equal to, or fx is equal to mx plus b, I could write this equation as fx is equal to mx plus b omega, omega being my second variable. Now it is this equation, which was a one-dimensional equation, becomes a two-dimensional equation. But I could take a specific point in my second dimension, that is, I'll choose omega to be 1, and the equation reduces back to the previous equation. But if I treat the equation in two dimension, this equation is a linear equation, while when I treat this equation as a single dimensional equation, it is a nonlinear equation. So increasing the dimensionality of the problem by one dimension improves the system and linearizes the system.
So affine transformation, what it does is that it combines a similitude transformation and linear transformation into a single group called the affine transformation. The only property of the affine transformation now is that it preserves parallel lines. So what you see here is that the previous preservation of distance is gone, the preservation of angles is gone. The only preservation that you see now is the preservation of parallel lines. And we will later see that when we do perspective projection, even parallel lines are not preserved and they start converging. So affine transformation is done by adding an additional dimension to my system. That is, if my function is a function of x and y, I add an additional coordinate w. So if it is a function is in 3 dimension, I have x, y, and z, and my fourth dimension would be my w. With this, I will be able to put the translation quantity into the matrix and show that it becomes a linear function. Right? Affine transformation are combination of linear transformation and translation put together. This is done by adding an additional coordinate system to the xyz coordinate. If I am dealing in 2 dimension, I add a w coordinate and it becomes a 3-dimensional coordinate system. If I'm working in 3 dimension, I add another coordinate system, it becomes a 4-dimensional coordinate system. And you can easily see that in the matrix shown here, C and F happens to be the translational quantity. Now this translational quantity will become a function of w, where it becomes a linear function of x, y, and w, and we can choose w to be 1, the property that is assuming just one point in my fourth dimension or the third dimension. I could do that. Properties of affine transformation. What we see is that the origin does not necessarily map to the origin. That is because translation has been incorporated. Lines map to lines. Parallel lines remain parallel. Ratios are not preserved. It is closed under composition. That is, you have an inverse of affine transformation. And there is a model change of basis. So above affine transformation, we will place our perspective projection or perspective transformation, where we will see that parallel lines are no more preserved and you have only thing that is preserved is the lines are preserved, and in each level, as I moved to the higher and higher level and to the final level, that is the perspective projection, is only that the lines are preserved while the other preservation relations slowly are removed from these sets as you generalize it to the final set, which is the perspective projections. We will see in detail perspective projections later on, where perspective projections depends on the way I look at the object. It depends on my eyes, which acts like a camera, and I see objects which are further away to be smaller in size, while objects closer to me look bigger in size. We will take up perspective projection in the later lectures, where perspective projection now, what we can say now is that perspective projection is a projective transformation, affine transformation, and a projective wrap, which it's a combination of affine transformation with a projective wrap. Properties of projective transformation are: origin does not necessarily map to the origin, similar to that of affine transformation. Line maps to a line But here parallel lines are not necessarily remaining parallel. Ratios are not preserved, but it is closed under composition, and there is a model change of basis that takes place. So what we have done is that we have learned about translation, which is part of the Euclidean transformation, translation, rotation, and identity transformation. I could have similarity transformation. From similarity transformation, I combine linear transformation with the similarity transformation to get affine transformation. And from affine transformation, I apply a specific projective wrap to get my perspective projection. The affine transformation and projective transformation will be looked at in a later lecture, where the operations are provided here. These transformations are nested set of group, closed under composition, and inverse is a member of the composition. Please note, scaling with S is equal to 0 is not